Hi, welcome to this lesson on Probability Counting Principles Part 1. Let's have a look at question 2. There are 3 different mathematics books, 2 different science books, 4 different history books, and 2 different economics books on a shelf. In how many ways can they be arranged if the order does not matter? So, we have 3 mathematics books, 2 science books, 4 history books, and 2 economics books. So in total, we have how many? 3 and 2 is 5, 7, 11. So there are 11 books in total on the shelf. So the total number of ways that they can be arranged if the order doesn't really matter is 11 books for the first position, 10 books for the second, 9 for the third, all the way up to 3 times 2 times 1. So that is 11 factorial. So let's go ahead on our calculators and check what is 11 factorial. Okay, so 11 factorial. Okay, so quite a big number. So let's write it out. Okay, so 39,916,800. Okay, so how do we read that? That's 39,916,800 different ways we can arrange those books. So it's quite funny when you think about it, right? There's only 11 books on the shelf, okay? But of those 11 books, if we kept placing them in different orders, there would be over 39 million possibilities of arranging them in unique ways. So that's quite fascinating. It's such a small number of books, but such a large number of possibilities because they grow quite fast. They grow through multiplication. Okay. What if all the books of the same subject must be next to each other? So let's say there are 3 mathematics books. Let's call them M1, M2, and M3. Then there are 2 science books. Let's call them S1 and S2. 4 history books. Let's call them H1, H2, H3, and H4. And 2 economics books. Let's call them E1 and E2. So each books in each group are unique books in their subject. So each of these can be arranged in 3 factorial ways, 2 factorial ways, 4 factorial ways, and 2 factorial ways. But then at the same time, these grouped objects counted as singular objects as well. There are 4 of them, and they can be arranged in 4 factorial ways. So the sub-objects are the books that are being arranged in their own subject criteria, and then the main objects are the grouped objects of each subject. So by the fundamental counting principle, the total number of ways is equal to 4 factorial, which is the total number of grouped ways, times the sub-object ways, 3 factorial, 2 factorial, 4 factorial, and 2 factorial. So let's put that into our calculator and see what we get. Okay, so let's just bring it up here a bit. Okay, so that's going to be 4 factorial times 3 factorial times 2 factorial times 4 factorial times another 2 factorial. Okay, and that's equal to 13,824. Okay, so there are 13,824 ways now that we can arrange all the books such that all the books of the same subject must be next to each other. And that's much smaller than that number we got previously, over 39 million. And again, because you can see there are restrictions happening. The restrictions mainly that the books of the same subjects must be next to each other. What if the 2 science books must stand first on the shelf? So again, let's think about this logically. There are 11 possibilities, 4, 5, 6, 7, 8, 9, 10, 11. But we know that the 2 science books, S1, S2, or it could be S2, S1. So essentially, there are 2 factorial ways, which is just 2. 2 ways you can arrange the 2 science books that must stand first on the shelf. But how many positions are left over here? There are 9. And we didn't impose any restrictions of how those 9 books must stand. So it must be 9 factorial. So the total way by the fundamental counting principle is 2 factorial times 9 factorial. So let's go ahead and do that. So 2 factorial is just 2 times 9 factorial, and we get 725,760. Okay. Again, the restriction here is far less weaker than the restriction that we did previously, where all subjects had to be next to each other. In this case, only the science need to be next to each other, and they needed to be first on the shelf, so the first 2 books. So it's a less of a restriction. So the weaker the restriction, usually the more number of possibilities. The stronger the restriction, so more restrictions, the smaller amount of possibilities. Okay. Lastly, what if we want the economics books to be next to each other? So now that's the only restriction. Just the economics books, they're the only ones that must be next to each other. So again, let's logic this out. Okay, so there are 11 ways, 4, 5, 6, 7, 8, 9, 10, 11. And we want the economics books to be next to each other. So can you see that the first option here is that the economics books could be here, E1, E2, or E2, E1. There are 2 factorial ways here. But then there are 9 factorial ways in the remaining space. Okay, so that is if the economics books go first. What if they go this way? So 3, 4, 5, 6, 7, 8, 9, 10, 11. Now what if we did in the second and third position on the shelf? So again, there's still 2 factorial ways. It could be E1, E2, or E2, E1. And then the remaining 9 spaces here, those are 9 factorial ways. So again, the first one is 2 factorial times 9 factorial, and it's going to be 2 factorial times 9 factorial. So let's think about this. How many positions can we keep moving over? Well, we can move over 1 position, then we could have the books being here. Okay, so there could be now 2 spots open, and then another 1, 2, 3, 4, 5, 6, 7. Okay, so there must be 9 factorial in total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there are 9 factorial still spaces, and then 2 factorial times the 9 books. Okay, so essentially, if we can count the number of spaces that these E1, E2s can move up until the very end here, then we are done. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So essentially we want up to this point here, where the 2 economics books are at the very end of the shelf. So let's count. How many times can this move over? Well, so this is one possibility. Then this is the second possibility, where we've moved over 1 space. Third possibility, we've moved over 2 spaces. The fourth possibility is that we're going to have 1, 2, 3 spaces now. Then we're going to have E1, E2, and then 6 more, because the spaces must always add up to 9 spaces left over for the other 9 books. Okay, then the fifth way, there's going to be 1, 2, 3, 4 spaces now. Okay, and then 5 remaining spaces over here. The sixth way is going to be 1, 2, 3, 4, 5 remaining spaces. E1 and E2 go in here. And there's 1, 2, 3, 4 left. The seventh way, there's going to be 1, 2, 3, 4, 5, 6 spaces, E1, E2, and then 3 spaces left. The eighth way is going to be it's going to be 7 ways, right? 5, 6, 7, then 8, 9. The ninth way is going to be 8 spaces, so 4, 8, 9, 10, 11. And then this is going to be the 10th position. So that 10th position is going to be 9 spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 2 books. So how many different possibilities? There are 10 possibilities times the 2 factorial in each way, right, for the economics books, times the other 9 spaces. But this 10 times 9 factorial is exactly 10 factorial times 2 factorial. So there's almost sort of like a general pattern we can spot. This 2 factorial comes from the number of books that we are interested in arranging, in this case the 2 economics books. And this 10 factorial comes from the fact that there will be 9 spaces left over, and it's just increased by 1, so 10 spaces. Okay, so there are 10 different possibilities, each with 2 factorial times 9 factorial ways or outcomes there. So by the fundamental counting principle, that's 10 factorial times 2 factorial. Okay, so let's do that. So 2 is 2 factorial, and then times 10 factorial. So that's 7,257,600. Okay, let's just double check that. Okay, so 2 factorial times 10 factorial is 7,257,600. Okay, so that's the total number of ways if the economics books must be next to each other. Awesome. I'll see you in the next one.